Swayam Prabha. Digital India. Educated India.
Welcome back. We are going to talk about the three most important things in an NMR that can give you very important or vital information for identifying a molecule or coming up with a structure for an isomer to literally lay the carbon framework of an organic molecule. We already talked about chemical shift. We are going to talk about spin-spin coupling. Well, spin-spin coupling is the most important part of the NMR because it gives us information about the neighboring hydrogens. So if you have two carbons connected by a sigma bond and you have two hydrogens, let's say on these, you may have more, I'm just taking an example, but let's say you have a hydrogen that is 3 bonds away. These two have a magnetic spin. These are charged particles that are spinning, which means they'll have a magnetic field that's generated. The magnetic field of this proton can interact with this proton. It's very complicated and it involves these sigma bonds, but we're just going to simplify it. And we'll call this spin-spin coupling. So we're going to talk about spin-spin coupling here. Spin-spin coupling is at the maximum when two hydrogens are back to back or eclipsed or have a 0 dihedral angle, or if they have a 180 dihedral angle. So those are the two places where you're going to see maximum spin-spin coupling. If the two protons are 90 degrees apart, you will see minimum spin-spin coupling. So for spin-spin coupling to occur, you have to have a certain angle. And you need to have a certain distance. They don't work over long range. You can have 3 bonds. In vinylic hydrogens, you can have 2 bonds. And in allylic, you can have 4 bonds. Typically, it doesn't really go beyond that. In some benzenes, you may have para coupling, which is actually 5 bonds. But other than that, most of the ones that we look at are 3 bonds apart. Okay, and so let's write down the definition. So we already completed this. We're going to talk about spin-spin coupling here. So an NMR signal can be split into multiple peaks. So instead of getting one blob, you get fine lines, multiple peaks, due to magnetic interaction, which we also call spin-spin coupling, between hydrogens that are on adjacent carbons that are non-equivalent. Okay. So that's very important too, that they're non-equivalent. What does that mean? Let's say you have a methyl group next to another methyl group. You have planar symmetry, axis of symmetry. So for the machine, these two look identical. They don't spin-spin couple. You get a single peak. However, if you have a carbon and a hydrogen and they have different things on it, let's say you have a chlorine and here you have a fluorine, like a fluorochlorocarbon, hydrocarbon. Now, these are two different environments. These are going to spin-spin couple. Okay, we are going to see the splitting pattern for this. So here you would see a peak for this and a peak for this because they'll have different chemical shifts. And these are going to split each other. And we are going to see what's the meaning of this and what does it take to give you these fine splittings. So let's look at some situations. Let's take a hydrogen that has no neighboring protons 3 bonds away. Let's say they are all carbons or halogens or things that don't have hydrogen. So that's one. So if you have no neighboring hydrogens, and we will call this neighboring hydrogens N, or that's the symbol, no N, or N here is equal to 0. Okay, so then you would have absolutely no spin-spin coupling here, and you would get a singlet. So here for this hydrogen that is in an environment where you have, and you may have this one or two, it doesn't really matter. If, let's say you have carbons here, and they are attached to carbons, halogens, some other groups, let's say all chlorines, and bromines or something that doesn't have any hydrogen. So here, this is two bonds here. Two bonds on an alkyl do not couple. So these two here are not going to couple. So let's say there are two protons on the same carbon and they're alkyl groups. They are not going to couple. So if you have two hydrogens with no neighboring hydrogens, these two on an alkyl group are not going to couple. Okay, so therefore both of these would only be a singlet. So here you would get a singlet. Let's say you have some chemical shift, and let's call that delta and A, and you will get one peak for that. Let's say these are your HA proton. At some chemical shift from TMS, you would get one peak. Let's say what happens if you have one neighboring hydrogen. Okay, so you have these having one peak. Now you're going to have a neighbor. Okay, let's look at another situation. One neighboring hydrogen. One neighboring hydrogen. A neighboring hydrogen is called N. N is equal to 1. Let's look at what happens when you have a neighboring hydrogen. So as we said before, when you have hydrogens on adjacent carbons, the spins can couple. So you can have two different scenarios. We know that when you in a magnetic field, there are two separate energy levels for a proton, two different spins. One can be in the direction of the field, and one can be in the opposite direction of the field. So here, let's say you have a proton. The proton can have the same spin as this. So it actually has a magnetic field that is in the same direction as this. You know, magnets have direction, or magnetic fields like north, south, and so on. And if they're also in the same direction as the magnet in the machine, then the magnetic field of this is going to enhance the magnetic field that this proton is going to feel. So when the magnetic field increases, the energy level increases, therefore the frequency would increase. So when you have a proton here, that is going to increase the chemical shift of this a teeny bit, okay, because the frequency is going to increase. So let's draw this out. So here is a carbon. This is your B carbon, let's say. And let's say this is your original H carbon. And here is a hydrogen, HA. And this is HB. So let's say when HA is going in one direction, and we will put that as that, HB can be going in the same direction. And therefore, it's going to enhance the frequency of absorption. Or you can have, for the same, let's say we're treating this spin in this direction, you can have an opposite spin for HB. So this is your HB spin. So that means you can have a spin that's going in the opposite direction. That is going to take away from this. So therefore, you're going to have a different frequency now. So this is your HA spin, and this is your HB spin. What you're seeing here is like a direction here with this blue sticker, and this is going in the opposite direction, as you can see with the red sticker. This is just a model, but you get the point. If it's in the opposite direction, then it's going to take away from this field. Therefore, your frequency is going to be a little lower. These are very, very, very tiny differences. in a hydrogen that is on adjacent carbon like that, that would mean a frequency shift about 6 to 8 hertz. That is called the coupling constant, because it is a constant for two protons on adjacent carbons in a molecule. So therefore, you're going to get two different values. So let's say this is going to be, let's say, nu1, and let's say this is going to be nu2. So if you didn't have any hydrogens next door, let's say HA had no neighbors, no N, then you would get just one peak, like over here, no neighbors. Since you have one hydrogen next door, HB, you can have enhanced field or diminished field due to the different spins. So therefore, now you're not going to have just a single peak. You will have an enhanced field at nu1 and a diminished field at nu2. That's absorbing at nu2. So instead of having one peak, now you're going to have two peaks. That is called a doublet. And the difference between these frequencies, nu1 minus nu2, that is called JAB, or coupling constant. And it's typically 6 to 8 hertz. So this is called the coupling constant. For two protons in a certain environment, okay, let's say these are halogens, let's say it's this molecule, then you will see that these are going to split each other and they are going to be a doublet. So this is going to split this into a doublet, and this will split this into a doublet. But we are only right now concerned about HA peak. So this is the peak for HA. Let's look at another scenario here. Let's see what happens if you have two neighboring hydrogens. So this is going to be a third scenario. Two neighboring hydrogens. N is equal to 2. What are the probabilities for that? So let's say we have over here a hydrogen, and you can have more hydrogens here. I'm just going to draw one just for simplicity. And instead of having one hydrogen next door, you have two hydrogens next door. So HB, there are two of them, and let's say I call that HB1 and HB2. They are identical, we're just labeling them. I'm just going to put X groups here, and X groups can be halogens, okay? Let's look at what could happen to this. So you have now, instead of having one hydrogen as a neighbor, you can have two hydrogens. So HB1 and HB2, just two hydrogens, they're identical, there's no difference, but they can have the same direction of spin as this. So they can interact with this in such a way that it's enhancing the field that this hydrogen experiencing. So here, when you enhance the field, then your frequency also increases. So this is one scenario where you have HA, HB, 1 and 2 all being in the same direction and in the direction of the magnetic field. So let's draw that out. So for when HA here spin is going in, let's say, this direction, I'm just going to put a up arrow for this spin. HB1 and HB2 can also go in the same direction. What are the other possibilities for this HB2? Well, there's also an equal probability that one of them can be going in the opposite direction. So let's look at that. So when you have a hydrogen here, it can have two neighboring hydrogens with opposite spin. So this is in the same direction as the hydrogen that we're looking at, HA, and this is in the opposite direction. This is going to enhance the magnetic field. This is going to diminish the magnetic field by the same amount. Therefore, there's not going to be really any shift in the frequency of absorption for this. Now we can also think of, a situation where it's reversed. This is opposite and this is the same. So here's the other situation where HB1 can be in the opposite direction and HB2 can be in the same direction. Let's write this down. So for when HA spin is in this direction, HB1 can be in the same direction, HB2 can be in the opposite direction, or HB1 can be in this direction and HB2 can be in this direction. Those are the only two probabilities possible, right? Now, this is going to enhance the field. So let's say this is going to absorb at a certain frequency. This over here, because you're enhancing and diminishing at the same amount, you are going to get a frequency that would be pretty much the same as if you had no neighbors. Now, what's the other possibility? The other possibility, of course, is when both of them are in the opposite direction of the HA that we're looking at. Okay, so here's the case where when you have a proton, it have two neighboring protons on adjacent carbons, and they can be in the opposite spin. Both of them are going to diminish the magnetic field experienced by HA. So if you have HA, let's say we are fixing HA in this direction, you can have HB both going in opposite directions. Now that would have a separate frequency. So here you have a 1 to 2 to 1 probability. So let's say we're going to do HA, a peak for HA. It's not going to have just one peak like here. It's going to be split into three different peaks at three different frequencies, which means when you take that frequency change from TMS, they'll also have different values. But the separation between this would be very small. It would be about 6 to 8 hertz. Right? So nu2 is where you would have a peak, and you will have nu1 and nu3. And this ratio between these peaks is going to be 1 to 2 to 1, because that's the probability of having those spins at any one point in time. So you get what you call a triplet. This is called a triplet. And the coupling constant here, this is going to be JAB. And they would be about the same as here, 6 to 8 hertz. All right, so we have a triplet, a doublet, and here's a singlet. Let's look at a third case scenario. Let's look at another scenario. Let's look at 3 hydrogen neighbors. So here, when you have 3 neighboring hydrogens, what is going to be your splitting pattern? N is equal to 3. Let's look at it. So you can have a hydrogen, and I'm just going to label this one A. You can have HA here as well. They're all going to be split by the same amount and by the same neighboring hydrogens. Your neighboring carbon is going to have 3 hydrogens, HB1, HB2, and HB3. Let's look at that. So what are the chances? Let's do the same thing again. All of these can be aligned in the same direction as this. Let's say this is spinning in this direction. All of these could be spinning in the same direction as the top one. So they're all spinning in the same direction and same direction. So if you have 3 hydrogens spinning in the same direction, they are all going to have magnetic fields that will enhance the magnetic field experienced by this HA. So that's going to increase it's a teeny amount, but it's going to increase the magnetic field experienced by this. Therefore, it's going to shift the frequency a little bit downfield. let's draw these out, this scenario. So here's HA, and let's say this direction of spin we can indicate by an arrow going up. HB1, HB2, HB3 can also at some point in time have the same direction as that. Now obviously you can have different spins or different directions of spin and different magnetic fields by HB protons at any one time. All right, let's look at them. Here's another scenario you can have for HA, which we are looking at, or any of these hydrogens here. You can have a situation where the field here generated by HB is in the spin is in the opposite direction, therefore that's going to diminish the field a little bit. These two can be in the same direction. That's one scenario. Let's write that down. So for HA going here in this direction, you can, let's say, have HB1 go in this opposite direction and HB2 and HB3 go in the same direction. We can have these switch around too. Let's look at that. All right, so we can have a situation where HB2 is in the opposite direction and HB1 and HB3 are in the same direction. So let's draw that out. So here this and this, these two are in the same direction. This is in the opposite direction. What are the other possibilities where you could have HB3 going in the opposite while these two go in the same direction as that? So here's a situation where you can have HB3 be on the opposite direction and HB1 and 2 be in the same direction. So there are three probable states for when one of the hydrogens is in the opposite direction of spin as the one that we are looking at. What else is possible? Well, we only flipped one. What about if we flip two of them? Let's look at that. Let's see what would happen if HB1 and HB2 are opposite. So let's look at a situation where you can have two of them flipped HB2 in the opposite direction as this. So they create a opposite field. So if HA, when it's spinning in this direction, you can have HB1 and HB2 be in the opposite direction and HB3 be in the same direction. That's one scenario. Or you could have HB1 and HB3 be in the opposite direction. HB2 can be in the same direction. That's another possibility. So this is going to have HB2 and these two can be in the opposite direction. Or, so we can see that HB1 and HB2 are in opposite direction, and at that particular moment in time HB3 is in the same direction. So we can have a situation where you have this kind of arrangement. Now the probability of having this is 3 times more than having this. Okay, now let's look at another situation. So we've explored all of the possibilities. What if all three are in opposite spins? Just like here they were all in the same spin, there's only one scenario that's possible here. So let's look at that. So for HA, there are 3 hydrogens neighboring and all 3 of them are in the opposite spin at this moment in time. When HA is going in the direction of, let's say, the magnet, these 3 are going in the opposite direction of the magnet. So therefore they're diminishing the field, so therefore you have one possibility for that. That means when HA is in this direction, HBs are all in the opposite direction. So here is a 1 and all these are probabilities for this 3 to 1. And you would see a peak representing this. So you would have over here a 1 to 3 to 3 to 1. The middle of this would be where you would have a peak for HA when you didn't have any of these. If HA is going to be a singlet, it would have been here. But these two actually are enhancing the field, therefore the frequency will be shifting a little bit higher and downfield. So this is going to be, let's say, nu 1, nu 2, nu 3, and nu 4. And that's what you will get. And the difference between these frequencies is what we call the coupling constant. And the coupling constant for all of these 3 bond couplings, constant in alkyl systems, is going to be about 6 to 8 hertz. So this is going to be the same. JAB is about 6 to 8 hertz. And if for a certain molecule where you have all of these groups fixed, the JAB is not going to change regardless of which machine you're running it on. That's going to be a constant. That is why we call it a coupling constant. All right, let's look at some trends here. What do we see here? We see that if you have, let's say, the numbering neighboring hydrogens, and let's see the splitting or multiplicity as we call it. Let's see the trend between this. This is also called splitting. When you have 0 hydrogens, neighboring hydrogens, you get a singlet, 1 peak. That's a singlet. When you have 1 neighboring proton, you have a double peak or a doublet. The splitting is 2. When you have 2 neighboring hydrogens, you are split into a triplet, 3 peaks or peaklets, triplet. When you have 3 neighboring hydrogens, you have 4 little peaks, or it's a quartet. So in summary, I'd like to say that if you don't have neighboring protons in an alkyl side chain, you would get a singlet. You rarely see 2 bond couplings in alkanes. If you have 1 neighbor, you're going to be a doublet. 2 neighbors, triplet, 3 neighbors, quartet, and so we can see there is a trend. Every time you add another proton to the neighboring carbon, your multiplicity will also increase by 1. So n plus 1 gives the multiplicity of the peak when you have n neighboring protons. Just one little thing, guys. I know we've been showing you these models and you might think these are very static molecules. It's just really the opposite. These are all spinning at hectic speeds. The protons are spinning. Then you also have the molecule having different conformations by spinning around sigma bonds, and these sigma bonds are spinning. So everybody here is spinning at breakneck speed. However, when we have these coupling constants, they are an average coupling constant between these protons. And the thing to remember is when you have, let's say, between these two, when you have a 0 degree dihedral angle, let's say the HA is in front and HB is at the back, and if you have 0 degrees between them, dihedral angle, or if you have 180 degrees between them, that's when you would have the maximum amount of coupling. When you have 90 degrees, that would be the minimum. So these are all average coupling constants, so that's something to remember. And let me draw that out. HA and HB are 180 degrees apart. These are 180 degrees apart. That's the maximum coupling, JAB max. 90 degree dihedral angle would be JAB minimum, maybe 0. So, and all of the coupling constants that you see here are averaged. I'll put averaged coupling constants. And there are other factors that would also influence them. For example, the groups that are here would also, influence the coupling constants. But they would typically be in this range, 6 to 8 hertz. So in summary, I'd like to say that if you don't have neighboring protons in an alkyl side chain, you would get a singlet. You rarely see 2 bond couplings in alkanes. If you have 1 neighbor, you're going to be a doublet. 2 neighbors, triplet, 3 neighbors, quartet, and so we can see there is a trend. Every time you add another proton to the neighboring carbon, your multiplicity will also increase by 1. And I will see you soon. And we will talk a little bit about integration. Thank you guys, and see you soon. Bye.